This program is brought to you by Stanford University. Please visit us at stanford.edu.
First of all, I want to show you what difference a sign can make, and in particular, the sign that occurs. We've studied an entangled state of two electrons. We could call it up-down. And then there are two possibilities. Well, there's more than two possibilities, but there are two interesting situations with a plus or minus. In other words, you can take your choice. We can study plus and we can study minus. Plus, minus, down, up. So this is two electrons. And the state that we're writing down is a linear superposition of states. In one, electron 1 is up. Let's call this 1, 2. Electron 1 is up. Electron 2 is down. So you know what that looks like. Looks like this. And in the other component of the state, you just flip them over. And we can superpose them with a plus sign or a minus sign. They don't sound so different. In either case, there's a good deal of correlation between the two spins. If one of them is up, then the other one is surely down. And if one of them is down, then the other one is surely up. In both cases, the probability, incidentally, nothing I'm going to say right now is going to depend on whether we should normalize it correctly. In fact, let's put the normalization in square root of 2 to make the probabilities add up to 1. In both cases, the sums, well, and what was I going to say in both cases? In both cases, the spins are opposite to each other, or the third component of spin is opposite to each other. So what is the big difference between these states? And they're quite different. They're quite different, and we want to spend a little bit of time explaining that. Before I do, let me write a list again, a list of the action of the various sigma operators. It's the same list that I wrote, same table that I wrote last time. First of all, sigma 1 on up equals down. We'll make reference to this regularly. Sigma 1 on down equals up. Sigma 2 on, what is it? Sigma 2 on up is, I believe, I times down. But sigma 2 on down is minus I times up. And sigma 3 on up is up. And sigma 3 on down is minus down. That's the action of the matrices sigma 1, sigma 2, and sigma 3 on the eigenstates of sigma 3 itself. So we'll make reference to that list as we go along. Now, in both of these states, the expectation value of any component of the spin, let's say sigma, we're going to remember now that sigma refers to the first electron, tau, which is an identical family of operators, identical except when it acts on the second spin instead of the first spin. So sigma and tau are the two spin operators. There's sigma 1, sigma 2, and sigma 3. And in either of these states, the expectation value of any component of sigma or tau is 0. So there is no direction in which either the first spin or the second spin is definitely polarized. There is no direction that you can pick that you will know that the spin has to come out up in that direction. That is, of course, different than any state that you would make for a single electron. And so this is some sort of entangled state that is not a simple juxtaposition of a spin in the state times another spin in its own state. They're mixed together in some entangled way. Okay, so first of all, every component in this state of the sigma i's are equal to 0, and the tau i's are equal to 0 in this particular state, and you can check that. I think we checked it last time, didn't we?
I think you showed that for the minus sign. Is it also true for the...
Yes, it's also true for the plus sign. You want to do it? We can do it. let's just, it's quite obvious for sigma 3. For sigma 3, there's one up electron and one down electron. No, let's do it. Let's do it. Why do I say that? Let's do it. Let's do, all right, so we have to take the bra vector up, down. Let's just write up, down, plus. Well, which one did you say I did? Minus. Okay, so let's do plus. Plus down, up. Let's put a bracket around it, or a squiggle around it. And now let's take, well, let's first take sigma 3. And then over here, up, down, plus, down, up. No, we've got to write the bracket the other way. And the square root of 2 doesn't matter here. If it's 0, it'll be 0 if we multiply it by square root of 2 or whatever. Okay, so what happens if we multiply this by sigma 3? Sigma 3 hits up and leaves it up. Sigma 3 hits down and changes the sign, right? So this is just going to be up, down, minus down, up. And I can leave out the sigma 3 now because I've just acted with the sigma 3 times up, down, plus down, up. Okay, so the inner product of up, down with up, down is 1. The inner product of up, down with down, up is 0. They're different. They're opposite. So right here we get a 1 from here, and then a minus 1 from here. Down, up with down, up, again, is 1, but there's a minus sign, so we get 0. Now, this does not mean that these states are eigenvectors of sigma 3 with eigenvalue 0. It means the expectation value of sigma 3 is 0. There's no eigenvectors of sigma 3 with eigenvalue 0. You can never get 0 for one of the spins. You can only get plus or minus 1. So it doesn't mean that when you measure any of the spins, you get 0. What it means is that it's measuring the spin is a fair coin toss where you get ups as much as you get downs in equal amount, equal probability. Okay, now I want to come to the difference. And the difference you can see most easily by considering an operator which is the sum of both spins. In other words, the spins represent little vectors, well, little pointers, excuse me, little pointers. Sigma might point that direction, tau might point that direction. They represent little magnetic moments. We could think about the magnetic moment of the combined system, which is simply the vector sum of the two magnetic moments, or the two spins. And so it's interesting then to look at the operator sigma 1, sigma plus tau, the three components of it, all three components of it. All right, let's see what let's see what sigma plus tau do to these two states. First of all, what is the action of sigma 3 plus tau 3 on up, down, plus down, up? Oops, up, down. Sorry, plus, minus, down, up. All right, the answer is 0. Why is that? First of all, one reason is obvious. In up, the spin is the third component of sigma 3 is up. In down, the component of tau 3 is down. So they add up to 0, but let's just check it. Sigma 3 acting on up gives plus up. Tau 3 acting on down gives minus. So sigma 3 plus tau 3 acting on up, down will give 0. Sigma 3 acting on up gives plus. Tau 3 acting on down gives minus. And so sigma 3 plus tau 3 definitely equals 0 for the left-hand state and also for the right-hand one over here. So the conclusion is that either of these states, in fact, just the two separate components here, are both eigenvectors of sigma 3 plus tau 3 with eigenvalue 0. That means if you measure sigma 3 plus tau 3, you will always get 0, okay, for either of these states. That's not surprising, since one is up and one is down. Okay, now what about sigma 1 plus tau 1? Let's do that little exercise. Sigma 1 plus tau 1. This is the sum of the first component, the x component of spin. Let's see if we can work out what it does to up, down, plus, minus, down, up. Okay, let's start with sigma 1. What does sigma 1 do to up? It turns it down, right? Okay, so sigma 1, let's write out everything that comes here. Sigma 1 on up, down gives us down, down, and sigma 1 and tau 1 on up, down gives minus. Tau 1 on down gives up. Sorry. So tau 1 gives up, up, plus up, up. That's what we get by applying sigma 1 plus tau 1 to up, down. Sigma 1 flips up, down, and makes down, down. Tau 1 flips down, up, and makes up, up. With a plus sign, because with a plus sign. The plus sign is this sign here. Then we have plus or minus. Okay. Then we have plus or minus. Let's see what sigma 1 does. Sigma 1 acts on down to give up, up, and then plus minus, down, down. Tau 1 flips up, down, and gives you down, down. Okay. The plus minus is the same plus minus that's here. Okay. All right, so it's quite clear that if we take the plus sign, we don't get 0. If we take the plus sign, we don't get 0. We just get twice down, down, plus twice up, up. The implication is that if you were to measure, the implication is that this is not an eigenvector of the sum of sigma 3 plus tau 3. You will not get 0 every time you measure it, even though its expectation value happens to be 0. If you measure it, sometimes you'll get, what are the possible values you can get? Sigma 3 can be plus or minus 1, tau 3 can be plus or minus 1, so it's clear the answer can be 2, 0, or minus, 2, 0, or minus 2. Is that right? That's all you can get, right? Yeah. But there would be no reason, and in fact it's quite clear, that you can't, that you don't get 0 every single time, because this is not an eigenvector of tau 1 plus sigma 1 with eigenvalue 0. So we can be quite sure then that this operator here does not give 0 every time you measure it, just because it is not an eigenvector in this state, just because it's not an eigenvector with eigenvalue 0. What about with a minus sign? With a minus sign in here. With a minus sign in here, that means we should put minuses, and the answer does vanish. Down, down, minus, down, down, up, up, minus, up, equals 0. So the state with the minus sign in here, let's concentrate on that one now. The state with the minus 1 here, every single time you measure sigma 1 plus tau 1, you get 0. Every single time you measure sigma 3 plus tau 3, there's two separate electrons. One of them you measure sigma, the other one you measure tau. You add the answers, sigma 1 plus tau 1, or sigma 2 plus tau 2, or whatever it is you measure. You always get 0 for the sums of the third components and for the sums of the first components. What about the second component? Let's check that one. And I won't do it for plus or minus now. We've already checked that sigma 1 plus tau 1 does not kill up, down, plus down, up. Let's see what happens if we put sigma 2 plus tau 2 on the same vector, up, down, minus down, up. All right, first of all, what does sigma 2 do? Sigma 2 multiplies the up here and makes it I times down. So the first entry will be I times down, down. That's from sigma 2 times this. Now, what about tau 2 times this? Tau 2 takes down and flips it up with a minus I. So that's minus I, up, up. Now, what about tau 2? Tau 2 takes down and flips it up with a minus I. So that's minus I, down, down. And then, with a minus sign, with another minus sign here, tau 2 takes up to down. Let's see, am I doing what I want to do? Where am I? We already have two down downs. Tau 2. Which one am I trying to do?
Tau 2 should be up, up.
Up, up. That's tau. That's this one. Yeah. And that should be I times up, up. Plus I times up, up. So again, it gives 0. Right. All components of sigma give 0. Furthermore, if I were to take, let's call it sigma dot tau, it's a little vector, sigma plus tau, not that, and dot it into some unit vector to take the component in any direction. Well, those things are built up out of sigma 1 plus tau 1, sigma 2 plus tau 2, and sigma 3 plus tau 3. So if we've checked that all three components of sigma plus tau are 0, and therefore sigma plus tau in any direction, whatever direction you measure it in, you will get 0.
For the negative?
Yeah, for the negative sign. The negative sign is called the singlet state. Why it's called the singlet state, maybe we'll get to, but for the moment it's called the singlet state. And it has the property that the sums of the little magnetic moments, the sums of the spins of the two particles, are exactly equal to 0 every time you measure it, in any direction. It happens to have the property that it's rotationally invariant. No matter what direction you measure it in, it always looks the same. But we see that in particular, specifically from looking at the various components of sigma plus tau. They're all 0. Okay. The implication of that, of course, is that if you measure a component of sigma, you'll instantly know what the same component of tau is. In other words, if we have an electron over there, Alice's electron over there, and Bob's electron over here, and Bob measures any component of the spin, he instantly knows what Alice will get if she measures the same component of spin. He won't necessarily know what's gotten by measuring some other component of the spin, but what he does know is if he measures any component of the spin and gets an answer, he instantly knows what Alice will get when she measures the other spin. Why? Because the sums of the spins in any direction are equal to 0. All right, so that's a... Yeah.
When you say same answer, you mean literally the same minus 1 plus 1, or on the average they will get the same probabilities?
Every single time. Every single time. And the reason is because this vector is an eigenvector of sigma plus tau. When it's an eigenvector, that tells you that every time you measure it in that state, you get the same answer equal to the eigenvalue. What's that?
That's for the singlet state.
For the singlet state, yeah. But not for the other one is called the triplet state. Why? Another issue we'll come to another day. So the singlet state has the special property that if you measure one spin, you automatically know that the other one is in the opposite direction. Okay? Meaning to say, you never measure the direction of a spin, you measure a component of a spin. Any component of the spin that you measure, if you measure the same component of the other spin, you will get the opposite answer. Okay? So that's a form of correlation. It's kind of similar to the penny and the dime. If I give Alice one coin and Bob the other coin, Alice looks at a coin, she instantly knows what Bob gets, but it's somehow deeper than that. It's not just the third component, the up-downness, but every single component, whichever one you happen to pick, in any direction, whatever, the two spins will come out to be opposite. Okay, that's a profound kind of correlation that, and it's called Einstein-Podolsky-Rosen correlation. Were Einstein, Podolsky, and Rosen the first ones to discover entanglement? No, not at all. I believe Schrödinger first discussed it, I think. In fact, I think he called it entanglement. And I think that was before. But in any case, let's go on. I want to go slowly. I next want to come to Bell's famous theorem. I can tell you the theorem is famous. What I can't tell you is whether or not it's profound or trivial. Not Bell's theorem, but Bell's inequality and the fact that quantum mechanics violates it. I cannot tell you. Half the days of the week, I think this is the most profound thing in the world, and the other half of the days, I say, oh, it's just another consequence of quantum mechanics. What I can tell you is that John Bell had exactly the same ambivalence to it, at least when I knew him. And I can tell you also that Richard Feynman had the same ambivalence to it. Some of the times it just seems so profound and so deep, and other times it just seems like, well, it's a trivial consequence of quantum mechanics. Of course it's true. You'll have to make up your own mind whether you think it's very, very profound or not. It gets a lot of press that it's the most profound thing since Swiss cheese, and sometimes, and you know, it may well be. In the end, it's going to depend on what the consequences of it are for future physics. At the moment, the consequences are just quantum mechanics works, that's all. And so without further ado, let's discuss. Oh, the theorem itself is quite trivial.
It excludes other theories.
Well, probably, yeah. It excludes quantum mechanics. The theorem excludes quantum mechanics. No, the theorem excludes quantum mechanics. In quantum mechanics, you can find violations of Bell's inequality. Bell's inequality is an absolutely classical theorem. It's a theorem about classical systems, completely classical systems. And when I derive it now, I don't want you to remind me anything about quantum mechanics because it doesn't have to do with quantum mechanics. We're going to derive a theorem about perfectly good classical logic. What is classical logic? Classical logic is basically set theory.
Going back to this Einstein, Podolsky, Rosen
Yes. No paradox yet.
Okay, whatever.
I mean, so far we've
Does
just...
that violate quantum causality? Or is that a separate issue?
No.
Since
It would violate causality if you could use it to send a message. If by Bob looking at the spin, Alice were to instantly know something that she didn't know before, that would violate causality. But she doesn't. She doesn't know anything different than... she has no more information than she had before. For example, if in this state, her spin half the time will be up and half the time will be down. That'll be true. Bob may measure his spin. She doesn't know anything. She'll look at her spin. Half the times it'll be up, half the times it'll be down. If she gets a message from Bob, and the message says, my spin is up, then she knows that her spin is down. But she's got to get that message, and that message can't be gotten faster than the speed of light.
are there any inertial time frames where one is in front of the other and the other's Bob measures first, and Alice measures first? Something like that?
No. Whatever Bob does, if Alice doesn't get a message from Bob, if she doesn't get a message from Bob, there are no implications for anything for her. She will have learned nothing from the fact that Bob made the measurement. She'll know nothing. She has to get a message from him to use the information that he has. If he sends her a message, I got up, then she knows it's down. But without that message being sent, she doesn't know anything new. So this is in no way a violation of causality, locality, or anything like that. That's one of the reasons that half the days of the week I think this isn't so profound. It doesn't violate anything deep or important in
A review. The singlet state is when you have the minus sign, and the eigenvalues are plus or minus 2 or 0.
Well, no, if you measure sigma plus tau in the singlet state, you get 0.
Okay.
In any direction, any component. It's in the triplet state, which is the one with a plus, where if you measure it, you can get 2, 0, or minus 1, or minus 2, excuse me. Okay, so let me tell you what Bell's theorem is. It's a very simple theorem. Supposing we have some objects, a whole collection of them, a set of things, and we look at the class of the objects that have certain properties, and I'm going to consider 3 properties. I'm going to call them A, B, and C, whatever they happen to be. They could stand for anything, any properties, A, B, and C. Let me write down the inequality first. In other words, each one of these little things, whatever it is, here's some set, and each member of the set has an A, a B, and a C. It has these properties. All right. Now I'm interested in the number of entities which have property A and not B. Not B is whatever the opposite of B is. All right. So if whatever the opposite of B is. The number of things which have property A and not B, plus the number of things that have property B and not C. And the classical theorem, which is so easy that I've never understood why there are long-winded proofs of it. It's basically very elementary, is greater than or equal to the number of things with property A and not C. Okay? The number of things with A and not B plus the number of things with B and not C is greater than or equal to the number of things with A and not C. How do you prove this? You prove it by drawing pictures. For one reason or another, in all the literature that I can find, they never draw a picture. It's all right. Let's draw the set, or let's delineate the set which has property A, the subset which has property A. Here's the subset which has property A. Well, let me do it the way I have it in my notes, so I don't screw up. Yeah. All right. Here's A over here. Let's call it A. Now, where is the subset B? The subset B may or may not intersect A. All right? If it intersects A, it means they have elements in common. If it doesn't intersect A, it means they don't have elements in common. But here's the subset B. And if B has no elements in common with A, it just means you should move. It just means that this region over here is 0. That there's no that there's nothing in here. All right, but in general there'll be something in here, which will be those things which have both A and B. And finally, C. Here's C. Now again, C may or may not have elements in common with A or B. If it doesn't, you just move it over a little bit so that it doesn't have elements in common with A, B, and C. But the most general situation is where it does have elements in common, but you lose nothing by pretending it has elements in common, because you can always at the end say that the elements in common are just a null set. There are just none of them. Okay, now let's also label. Put some color in here. Let's also label all these various individual little subregions here. Let's see what I call them. Okay, this region out here is just 1. What is that? That's all of A, which is neither B nor C. And I'm just going to label all the various sub-areas in here. 3, 4, 5, 6, and 7. And of course, there may be some elements which have neither A, B, or C, and they'll be out here. But I don't even need to write those down because I'm not interested in them. Okay, let's take the number of elements that have A and not B. That has A but does not have B. What is that? That's region 1 and 2. If it has A but it doesn't have B, that means it's A but exclude anything that has B, and that means that it's the number that's in 1 plus the number that's in 2. Everybody see that? Okay, so the first thing here is N1 plus N2. That's NA, not B. Now, what about the number of B, the number of systems which has B but not C? So we go over to B, and we exclude those that have C. 5 and 6 have C. So in looking at B, the things which have B but not C, what are those? That's plus. Things which have B but not C. 4 and 7, right? Plus N4 plus N7. Now, what about N and not? What about A and not C? A and not C is 1 and 4. A and not C is 1 and 4. Did I get that right? Sorry, what I want to write here is greater than or equal to. No, what did I wrote something wrong. A and not C. Say it again? This one, N, which one? N7. Right? Do I have it right? I think so, yes. All right. Well, obviously, here's N1, here's N4. Obviously, N1, and all the N's are positive. I mean, there's no such thing as a negative number of elements. Right? N1 plus N2 plus N4 plus N7 is certainly bigger than N1 plus N4, or equal to it. At worst, it's equal to it. That's Bell's theorem. That's the whole thing. That's it. What's amazing is that it's violated. It can be violated.
That's profound.
The violation is profound.
Yeah, but all of quantum mechanics violates classical physics. So I mean, yeah, as I said, I've always been ambivalent, and I'm never going to get unambivalent about it. I'll die being ambivalent to it.
So you get in quantum state yourself when you think about it.
That's when I start thinking it's profound. Yeah. Okay. Let's now take our system to be 2 spins. Let's take our system to be 2 spins, and then we'll define the various properties A and B, A, B, and C, which we'll think of. Incidentally, we're imagining. Let's see. We'll first pretend that the spins are classical, and that you can measure them as if they were classical objects. And we'll write down what Bell's inequality says for the system of 2 spins. The only thing you need to know, and you have to keep track of, I'm going to talk about spin 1. I'm only going to talk about spin 1. But what I'm going to say is we're going to say things like, here might be a proposition. A proposition might be that spin 1, let's see, I guess, how did I label this? Spin 1 is up along z-axis. along the third axis. That could be some proposition. Right? Well, the negative of it is spin 1 is not up along the third axis, but of course that's the same as saying it's down along the third axis. But if spin 1 is measured down along the third axis, then you can be sure that 2 is up along the third axis. So the negative in the singlet state, we're putting the electrons into the singlet state, all right? And if classical logic, if ordinary logic made any sense, here's what we would do. We would measure, we have a whole beam of these electron pairs, zillions of them, zillions of pairs, which are each correlated in this fashion, separate from each other. And you measure the first 100,000 of them in every possible direction. You measure sigma 1 and tau 1, you measure sigma 3 and tau 3, for many, many of them. And you convince yourself, after a long, tedious bunch of experiments, that every time you measure a component of this spin and you measure a component of the same component of the other spin, that they're always opposite to each other. In that case, I think we would all agree that the negative of saying, or the opposite of saying A is up, is saying that B is up. Because if A is down, then B is up. Right? So the negative of a proposition about one spin becomes the positive statement about the other spin. So the negative of spin 1, spin, what is it called, A or 1, I forgot. The negative of calling this spin, the negative of this spin being up is the spin down, but then it's the same as saying that the spin is up. Okay? So we just have to keep track of of the relationship between these various propositions. Okay, we're going to write down what A, B, and C are. A, and we're only going to talk about spin 1 at first. But then we're going to use spin 2 to tell us something about spin 1. All right. So A is up along 3 axis. That's A. Okay. B, this equal sign here just means is the statement that spin 1 is up along the third axis. B is that spin 1 is up along a 45-degree angle. The 45-degree angle could be in the ZX plane. In the ZX plane, for example. Let's take it to be in the ZX plane. So B says spin 1 is up along the 45-degree angle in the ZX plane. And C says that 1 is up along the 90-degree direction in the XY plane, in the ZX plane. Okay, so here's our picture. A says that the spin is up along the third axis. B says that it lies at 45 degrees along the along that axis, and C says that it lies at 90 degrees along that axis. A, B, C. Okay. Now, what about not B? Let's take not. Well, first of all, let's take not A. I don't think we need not A for anything. We will need not B. Not B says that 1 does not lie. That the spin is not up along the 45-degree axis. It says it's down along the 45-degree axis. But then it says that spin 2 is up along the 45-degree. All right, so not B is that spin 2 is up along 45 degrees. Not B. B is that 1 is up along the 45 degree. Not B is that 2 is up along the 45 degree. Okay, you get the idea? Same thing for C. Not C is that 2 is up along 90 degrees. Okay, so now we can plug into here what these various statements say.
Down.
No? Not C. Let's see. C says that 1 is up along the 90. Not C says 1 is down along the 90. But then 2 is up. Okay? So whatever the statement is, the not of the statement is the original statement except made on the other spin. Okay? Is that clear? The other spin is in the opposite direction. That's all it says. So whatever a not statement is, it becomes a yes statement about the other spin. Okay. So let's write down what this says. All right, this says the number of pairs, the entities now are pairs of electrons. Pairs of electrons. This becomes then the number of pairs with spin up, let's call it, spin 1 is up at 0 degrees. Up at 0 degrees. And the other spin, let's see, we want not B. Not B is that the other spin is up along the 45-degree angle. All right, so the second spin, this is the first spin. Here I'm writing in the second spin. Up along 45 degrees. All right. A is that spin 1 is up along the third axis, and not B is that spin 2 is up along 45 degrees. Yeah, this stands for electron 1, this stands for electron 2. Okay? The first entry here is electron 1, the second entry here is electron 2. Next, B not C. Now, I don't have to worry about B not C, and I'll tell you why. It's got to be exactly the same as A not B. Why is that? A not B and B not C are simply related by rotating by 45 degrees. Anything I can say about A and not B will be exactly the same as B and not C because they're identical to each other except for a rotation by 45 degrees. Okay? And the singlet state doesn't change if you rotate it by 45 degrees. That's the main thing about it. It doesn't change when you rotate. We saw that by seeing that the spin, total spin, is the same in every direction. So in fact, we can just take this to be twice. The sum of this and this are just twice the number of up at 0 degrees and down at 45 degrees. And Bell's theorem, if it were true, would tell us that this is greater than, necessarily greater than or equal to the number of pairs with the property that they're up. This should be, C should be, did I write C correctly? Yeah. Yeah, C is up along 90 degrees.
Right, A is 1 up at along 3.
Along 0.
What's that?
Along
A
the
is
z-axis.
1 up at 0.
1 up at 0 for the first.
Yeah, okay, so right. A is 1 is up at 0 degrees. And not C means 2 is up along 90 degrees. 2 is up at 90 degrees. Well, now we have something we can test. Incidentally, counting the number of them is the same as counting the probability for these things to be true. If we have a large number of identical things in an ensemble, measuring the number is just measuring the probability. Okay, if we have 100,000 pairs, the number which has a certain property is just a certain percentage of 100,000, which is given, the percentage is given by the probability. Okay, so here's the question then. In the singlet state, what is the probability? What are these various probabilities? The probability for first electron to be up at 0 degrees and the second electron to be up at 45 degrees. How do we calculate that? All right. I want to, here's a question. I'm going to tell you the answer right now. The answer right now is that this is less than this when you calculate it. We're going to calculate it. But this is less than this, and it simply violates the very, very elementary theorem that Bell, it's hardly a theorem. It's just a very simple observation about probabilities. Okay. Let's see if we can calculate these things. What I need to do in order to calculate them efficiently is to teach you about projection operators. So let me tell you what a projection operator is, and let me give you an alternative definition of the probability postulate of quantum mechanics. A projection operator, it's labeled like that, projection operator, P for projection operator, has a number of properties. But first I'm going to tell you I'll give you a picture of what it does. What it would do in an ordinary projection operator in three-dimensional space, if my vector space happened to be just vectors in 3 dimensions, then there are subspaces. A subspace of 3-dimensional space could be 0-dimensional, that's just a point, just the origin, nothing at all. It could be a 1-dimensional subspace, which is just a line sticking out of the origin, or a 2-dimensional subspace, which is a plane passing through the origin. If you like, it's the space which is, well, you get it. If you have a 2-dimensional vector space would be take any pair of vectors and think of all the vectors that you can make by adding these two with arbitrary coefficients. All those vectors will lie in the plane of those two vectors. That's the subspace which is spanned by 2 vectors. If I have only one vector and that's a 1-dimensional subspace, then it's all the vectors that lie along a line. If you have a higher dimensional subspace, then, a higher dimensional space, then you can have subspaces up to the dimensionality of 1 less than the space itself. All right, what is a projection operator? A projection operator, in particular a projection operator onto a 1-dimensional space, in particular. It's an operation which takes any vector and takes its projection onto that subspace and gives you the vector which is the projection along the subspace of the original vector. It's an operator, so it will operate on a vector, let's call it alpha, to give you the projection, let's call it alpha sub p, onto the appropriate subspace. If the subspace is this line here, then it would act on any vector to give you the projection onto that subspace. Okay. So that's what it does. It takes away, it removes the components of a vector in directions perpendicular to the subspace. It just chops them out and removes them. Okay. Let's see. How about projection onto a 2-dimensional subspace? A simple 2-dimensional subspace would just be, let's say, the xy plane. Just the xy plane here would be a 2-dimensional subspace. If I have an arbitrary vector, then it just projects onto the plane and gives you the projection onto the plane. Okay. That's the notion of a projection operator. Now, suppose we have some property that we're interested in. The property is, let's take the property to be, the spin is up along the 3rd axis. There's an eigenvector that goes with that, the up eigenvector along the 3rd axis. Therefore, there's a projection operator that goes with that statement. The statement that the spin is up along the x-axis corresponds to a projection operator. It's the projection operator which projects onto the eigenvector in which the spin is up along the 3rd axis. Okay? So what does it do? It takes any state, the projection operator that projects onto spin being up, for one spin. Let's just talk about one spin. What is that? It's an operator which takes any vector, let's call it alpha beta, and what does it give? This is projection onto sigma 3 equals 1. Projection onto sigma 3 equals 1. What does it give?
side is? Where it intersects the what? The vertical axis?
No, it just throws away beta.
Oh.
It just throws it away. Beta is orthogonal. The state with the lower entry here is orthogonal to the state in which the spin is up. Okay? So all it does is it picks out the component of the vector along the particular property that you're interested in. Right? So it just gives you alpha 0. It throws away the piece of the vector that has to do with spin being down. What does P3 equal minus, sorry, P sigma 3 equals minus 1 do on the same vector? It throws away alpha. All right, here's an alternative formulation. What's that? Sigma 3 equals minus 1, excuse me. Incidentally, P is an operator. It operates on a vector to give a new vector. There must be a matrix that goes with it. Let me tell you what the matrix is. Okay. The projection operator onto sigma 3 equals plus 1. That's the matrix 1, 0, 0, 0. Let's check that. Suppose that acts on alpha beta. What does it give? It gives 1 times alpha and 0 times beta. 0 times beta, okay? So that's true. There's another way to write it, which is going to be very efficient, and we're going to find it very, very useful to write this operator in the form sigma 3 plus 1 divided by 2. Let's check that. Sigma 3 is 1 minus 1, 0, 0, plus 1, which is 1, 1, 0, 0. The 1 placed in the lower element here vanishes, minus 1 plus 1, and then divide by 2. Okay? So in the upper entry here, you get 1 plus 1 is 2 divided by 2. That's 1. And every place else you get 0. All right? This is a useful fact that the projection operator onto a configuration where the third component of spin is plus is just sigma 3 plus 1 divided by 2.
What about things like sigma 1 or sigma 2?
What's that?
What about projections corresponding to sigma 1 or sigma 2?
Yeah, okay, so now let's ask that question. What would you expect the answer to be if I asked you what's the projection operator that projects onto the eigenvector sigma 1 equals plus 1?
Sigma 1 plus 1 over 2.
Exactly. This is projection operator for, let's just call it projection operator for sigma 3. Here's projection operator for sigma 1. And by that I mean that sigma 1 is equal to plus 1. That's just equal to sigma 1 plus 1 over 2. You can check that. Easy to check. It's very easy to check. That's the projection operator. So let me give you now an alternative definition of the probability postulate of quantum mechanics. If you have a state, an arbitrary state, let's call it psi, and you're interested in the probability that a certain thing is true, or that you measure it that a certain thing is true, you construct the projection operator for that certain thing. You call it P. The expectation value of the projection operator is the probability for that thing. Probability for alpha. Let's just check that for a simple case. Supposing again psi is just alpha beta, is just a vector alpha beta, and P3 is sigma 3 plus 1. Okay, so here we have alpha, beta. We have sigma 3 plus 1 divided by 2, and then we have alpha star, beta star. This is the expectation value of the projection operator. What do we get? Well, what does sigma 3 do on this vector here? It multiplies the alpha by 1 and the beta by minus 1, right? So what it gives, when sigma 3 plus a half, sigma 3 plus 1 divided by 2 acts on this vector here, it just gives something simple. Sigma 3 plus 1 divided by 2 gives plus 1 on alpha. And what does it give? It gives 0 on beta, right? This gives 0. It just, we already know what it does. It just gives this. Times alpha star, beta star. This is just equal to alpha star alpha. So there's an example where calculating the expectation value of a projection operator gives you the probability, in this case, for the spin to be up. So this is an alternative definition of the probability assumption. If you're interested in a certain proposition, alpha is true, you construct the projection operator for alpha in the way that I showed you. It's the projection operator onto the direction, which is the eigenvector corresponding to the proposition, and then you just calculate its expectation value. That gives you the probability. Okay. Very simple, an alternative route to getting to probabilities. All right, so now we have everything we need to calculate the various probabilities that are in this expression here. Shall I stop from? Let's stop for a little bit. Let's stop for a little bit. Probably getting a headache by now. Okay, look, let me simplify what I said down to its bare essentials. Projection operators correspond to statements. Well, let me go back a step. Classical physics. Statements are subsets. Properties are subsets of a set. The set of all things, we start with the set of all things. The set of all things such that, that's a subset. The basic ideas of intersection and union and all those kind of things about sets and subsets are classical logic. That's what classical logic is about, the classical logic of propositions. Propositions mean properties of systems in physics. In quantum mechanics, a very, very different setup. Propositions do not correspond to subsets. They correspond to subspaces of a vector space. Subspaces of a vector space are a very different thing than subsets of a set. And therein lies the very big differences, and therein we're going to see allows us to calculate, well, we're going to use the fact that properties correspond to projection operators. Or you can say that they correspond to subspaces, the subspace of states which has this or that property. And for our purposes now, the only projection operators that I'm going to be interested in are the ones which correspond to spin in a given direction being up. Okay, so the projection operator for, let's start with, where's our, anybody remember what A, B, and C were? I don't. Oh, yes, here it is. All right, A was, the first spin is up along the third axis. All right, what's the projection operator for this? It's sigma 3 plus 1 divided by 2. That's only half the statement, though. The second spin is up along the 45-degree axis. All right, what is the projection operator for that? Anybody know? The 45-degree axis, what's the spin, what's the component of spin along the 45-degree axis, first of all?
Square root of 2, I don't know.
It's something like tau 1 plus tau 3, right? I mean, it's along an axis halfway between 1 and 3. Right? So that's tau 1 plus tau 3, but that's not quite right. What's wrong with it?
You can normalize it.
1 over the square root of 2. Here's what we're doing. We're taking n, the unit vector, along 45 degrees and dotting it into tau. All right, what the components of n along 45 degrees? They're 1 over the square root of 2. So this is tau 1 over the square root of 2 plus tau 3 over the square root of 2. That's the component of tau along 45-degree axis. All right, so it's the projection operator for the second statement here is tau 1 plus tau 3 plus over the square root of 2 plus 1. What I'm using is that the projection operator for sigma dot n is just sigma dot n. The projection operator is sigma dot n plus 1 over 2. That projects you onto the subspace in which sigma dot n is plus 1. Yeah, whole thing has to be divided by 2. Thank you. Good. Okay. Now, if you apply both projection operators to a state, this one acts on the first spin and projects the state onto the component, or it acts only on the first spin, and takes away anything in which sigma dot 3 is in the wrong direction. And then if you act with this one second, it takes away anything on the second spin which is in the wrong direction. So the whole projection operator that corresponds to this combined statement that, that the first spin is up along 0 degrees, the second spin is up along 45 degrees, is just the product of these two. You act first with one of them, that throws away everything in the state vector that's in the wrong direction in the space of states. And then you act with the other one that throws away everything that's in the wrong direction corresponding to the other spin. So the product of these two is the projection operator that projects out, or that projects for you, up along 0 degrees for the first spin and up along 45 degrees for the second spin. And remember, that's A and not B. Not B because B, you remember, B corresponds to up along the 45-degree axis. Not B corresponds to down along the 45-degree axis. But then we look at particle 2 instead of particle 1, and particle 1 always has the opposite spin, so it becomes up along the 45-degree axis for spin number 2. This is the projection operator for this object, for this property over here, for the property that A and not B. Okay? All right. Its expectation value in the singlet state corresponds to the probability for A and not B. All right, so all we can do, there's only one way to do this, and that's to just hold your breath and start writing and working out the details one by one. I'm going to do it. This is tedious. It may bore you. You can close your eyes, and I'll tell you what the answer is, but you might as well see how it's done for those who are really interested. For those who aren't interested, no, you can go home. Okay, so let's write down the singlet state here. The singlet state is up, down, minus down, up, and now we better put in the square root of 2. Now later on, we're going to take the inner product of what we have and project it back onto the same vector. So later on, we're going to project back onto the singlet. All right, but for now, I just want to calculate what this operator does when it hits this state. Okay, it's actually not too bad. First of all, what does sigma 3 plus 1 do to this over here? Yeah, it just throws this away. Why? Because in this state here, the first spin is down. But this is the projection operator onto the first spin being up. So when sigma 3 plus 1 over 2 acts on a state where the first spin is down, it just kills it. So we might as well get rid of that. Okay, and now we've done it. We've used sigma 3 plus 1 over 2. So we can now rewrite this. I won't erase it, but I'll write it. We get rid of this. We've acted with it, and it just kills the second entry here. The rest of it is tau 1 plus tau 3 over 2 root 2 plus 1/2 all acting on 1 over the square root of 2. Well, let's put another 1 over square root of 2 out here. That's this one. And then that acts on up, down. Okay, what does it do? First of all, what does tau 1 do? Tau 1 flips. Now remember, taus act on the second entry. Tau 1 flips down to up. So when tau 1 acts, it gives up here. Okay? What's in here? Is there anything with up in here? No. No, nothing with up in here. All there is up, down, and down, up. So that means when tau 1 acts, it gives something which is completely orthogonal to what's on the left-hand side. It won't contribute. When we take the inner product with the singlet, when tau 1 occurs and acts on down to give up, it'll give something on the right-hand side that just doesn't appear in the corresponding bra vector. So we can be quite sure then that tau 1 will have no expectation, will just not contribute to this inner product. I can throw it away. What does tau 3 do to this?
Is it minus down? Down is minus 3 down. Is it minus down?
Minus. Yeah. Tau 3, remember, tau acts on the second entry here. Tau 3 measures the component of the second spin, and the second spin is down. So that's just minus 1. When it acts on down, it just gives minus 1. It just multiplies it by minus 1. So this just becomes minus 1. That's it. It's just a number. The whole effect of all of this stuff here is to throw away the second state. That's sigma 3 plus 1. And the tau operation here just gives this number. Now, that's not quite true. There's another piece. There's the up piece, but the up piece will not have anything to take it in a product with. All right, let's write down the singlet state on this side. The singlet state on this side is up, down, minus down, up, divided by square root of 2. Well, the down-up configuration won't contribute. It's orthogonal to up-down. Down-up is orthogonal to up-down. So this one will not contribute. We can get rid of it. The inner product of up-down with itself is just 1. So the whole thing is just given by these numbers, 1 over square root of 2, 1 over square root of 2, and this beast over here. This is the probability for A and not B. So what is it? 1 over square root of 2? No, it's 1/2 minus 1 over 2 square root of 2. Anybody can do numbers quick in their head?
1/4 of the square root of 2 minus 1 over 2.
Yeah, 1/4 of, what do you have, 1 minus 1 over square root of 2? Is that right? All right, 1 over square root of 2 is about 0.7. 0.7, right? 1 minus 1 over square root of 2 is 1.4. 1 over 1.4 is about 0.7. 1 minus 0.7 is 0.3. So this is 0.3 over 4. How big is that? 0.075? 0.075, right? But remember that we have twice that. This one and this one are equal, and so we have twice that. So this number here is twice 0.075, which is what? 75 and 75 is 150. 0.15? 0.15. Nice and small. Now let's calculate this one. Okay? This is, all right, we'll just do it on the same construction here. All right. We still have one we still have electron 1 up along the 0 axis. That's this. But now we have electron 2 is up along 90 degrees. 90 degrees means the 1 axis. The projection operator for the 1 axis is just tau 1 plus 1 over 2. Now, I'm not going to erase this. I'm just going to doctor it up so that it corresponds to the second statement over here. So let's see. So we can get rid of the tau 3. It's just tau 1 over 2 plus a half. That's it. Okay, let's... okay. Again, sigma 3 plus 1 over 2 again gets rid of this term here. It picks out the component of the state in which the first spin is up. So nothing new as far as that's concerned. And now let's see what tau 1 does. Tau 1 takes up down to up. So when tau 1 acts, it makes up, up. But there's no up, up on this side here. So this one doesn't contribute at all. Let's see, this is not minus. This is just plus a half. All right, so the tau 1 doesn't give anything either. Tau 1 acting on down gives up. You have up, up here, but you have no up, up over here. So that's dead. And all you get is 1/2. This is it. Sigma 3 plus 1 did nothing. All you got was 1/2. And now you got some square roots of 2. You have a square root of 2 from here, and you have a square root of 2 from here. So the whole thing is 1/4, 0.25. This thing here is 0.25. Well, 0.15 is not bigger than 0.25. We went through this whole exercise to see that the right-hand side here is bigger than the left-hand side. This is what John Bell did. As far as I know, it's the only thing he did in physics, but it's pretty brilliant. The little exercise in quantum mechanics here is one you can go home and redo for yourself. But the upshot is that, that the quantum singlet state of a pair of electrons violates Bell's theorem, Bell's inequality. What does that mean? That means that there is no possibility that there's an underlying classical way of thinking about quantum mechanics where properties are somehow governed by ordinary set theory. There's no possible underlying description of classical underlying description of quantum mechanics. It cannot be the statistical theory of some complicated, chaotic, jumbled classical system.
Yeah. So you don't need to do any experiments if you already have quantum mechanics, and then you know Bell's inequality is not going to work. You don't need to do those experiments.
Absolutely.
So aspect, whatever his name is, did all these experiments for nothing?
Well, the question is whether or not nature follows quantum mechanics.
No. Everybody knew that nature follows quantum mechanics. I mean, you know, quantum mechanics has been tested to very high precision. Let's put it this way. Well, it's a beautiful experiment. I'm sure it was fun to do. Did it teach us anything we didn't know? Well, it might have taught us something about the technology of manipulating electrons, and I suspect it did, and I suspect it was a hard experiment. It was a very delicate experiment, and so it probably is part of the march toward being able to manipulate small things. I think in that sense, it was a piece of technology. Was the result certain beforehand? Absolutely. I mean, you know. Yeah, I mean, no, the experiment could not have, quantum mechanics has been checked in so many ways before that nobody expected. Now, I'll tell you what aspect did do, which is a hard thing to do. It's a hard thing to do. What it checked, here's what you would want to check. Okay, is there an out? Is there an out? Is there any way that classical logic could somehow simulate quantum mechanics? And the answer is yes, but only if the system that you're talking about sort of has wires connected with the left electron to the right electron in some way that makes the experiment on the left not independent of the experiment on the right. If you had somehow that when you did the experiment over here, some signal went over here and told it to rearrange and do something complicated. In other words, if you have a whole bunch of wires coming from the left and the right and they join together and you have a processor in the center, you can simulate quantum mechanics. But it's at the cost that signals have to be able to go faster than the speed of light. That if you had any classical system that could somehow detect what you did over here and send the message quickly over to there instantly before the second experiment, or in other words, if Bob could send a message to Alice instantly and tell her what's going on, yes, there are ways to simulate quantum mechanics classically. So the second element of this is that the experiments on the left and the right that measure the two components of spin really are independent, that they're far from each other and couldn't have interfered with each other. Now, one way of making absolutely certain that they couldn't have interfered with each other is to make all of Alice's experiments take place right basically at the same time or very, very shortly after Bob's experiments. If Alice's experiment takes place at a time for which light could not have traveled from Bob, then Alice's experiment must be independent. No wire could have sent a piece of information. There would be no way that any classical signal could have been sent from one to the other. So one of the things that was in Aspect's experiment was not just that taking these singlet electrons and measuring them and so forth, the left one and the right one, and checking whether the inequality was satisfied, but he managed to do it in such a way that there was no ambiguity that Alice's electron was measured sufficiently soon after Bob's electron that light could not have propagated between them. That was the hard part of the experiment, as far as I know, to be able to do both experiments sufficiently simultaneously that there was no possibility of information flow, classical information flow from one to the other. So the two experiments of Alice and Bob were, in that sense, independent of each other, under the assumption that no signals can travel faster than the speed of light. All attempts to simulate quantum mechanics from classical underlying logic always make use of some non-local assumptions, some kind of thing which can process signals at one end and send them to the other end essentially instantaneously. So I think that was the hard part of Alan Aspect's experiment, was the timing issue, I think. And I think that was the sort of technological triumph that they were able to be quite certain that the second experiment was done within the transit time of a light beam from the first experiment. No interference between them, yeah.
Didn't Bell do this after Einstein died?
I suppose, yeah. Sure.
Like the,
Yeah.
So, but Einstein, what did Bell do that clarified this?
He just made a very quantitative statement. A very quantitative statement. Einstein had this idea. Somehow this is funny. Well, what was spooky? What was spooky about it? This is what was spooky about it. That it violated a classical logic proposition. Now, it's not surprising that you can violate classical logic propositions. Quantum mechanics is not classical logic, but he just pinned one down. He just pinned one down very, very solidly and was very quantitative about it. The fact that the experiment was done was probably less important than he put his finger on a thought experiment that could be done, which would, if it were done, would rule out a classical underlying basis. He didn't have to do the experiment. He said, no, this is enough. This is enough. I know that quantum mechanics will work for this, and therefore I know that quantum mechanics cannot have an underlying classical basis. He was very ambivalent about all of this. I mean, some of the times he thought this was brilliant, some of the times he thought, oh, it's trivial. And then toward the end of his life, he thought it was so brilliant that he began to question quantum mechanics and began to question whether quantum mechanics was the right theory. But yeah.
But what interests me, this isn't a question, but maybe you can comment on it. Usually you think quantum mechanics is really tiny things, but here you've got two electrons that are flying apart, and that could be miles apart.
Yeah.
And yet still have a common wave function.
Yeah.
So now it's really large things that we're talking about.
Well, it's small things far apart. I mean, you couldn't do it with two bowling balls. Let's put it that way. But your point is well taken. But I mean, you still it's still about small things. But the small things, you have to be careful to keep the quantum wave function intact when you take things apart. When you take things apart, disturbing influences can ruin the wave function. For example, just the atmosphere, in interacting with the atmosphere, can do things to the wave function that ruin the experiment. So when you take them apart, it's very delicate. You better do it in a vacuum, you better do it cold, you better make sure that there's no photons around that can interact with the electrons, and care is required. And the further you take them apart, the more care that's going to be required, because the quantum wave function tends to get out of sync, not by itself, but by interaction with other things, interaction with an environment. I think we'll try to talk a little about interaction with an environment.
So the idea that you could measure something about that second electron just by looking at the first one, right? And so therefore, Heisenberg's uncertainty principle, the way I think Heisenberg understood it, wouldn't be valid.
Well, no, I mean, this is a trick which makes it look like you're violating Heisenberg's uncertainty principle. But it is still true that you cannot directly measure certain simultaneous properties about one electron. You really haven't done that.
You can measure the position of one of them and the velocity,
velocity
of the other
of
one,
the
presumably.
Yeah, nobody's going to stop you from doing that. You can do that, but it's not quite the same thing as measuring the position and velocity of one electron. And in fact, I mean, there's a theorem that you really can't make a machine that will replicate a quantum system with another one just like it. In fact, we could prove that theorem right now if we want. I'll do it in a minute. Well, should we do the no cloning theorem? All right, do it in a minute. Yeah.
In your argument, you use the product of two projections to simulate the end of two propositions. So does that mean that the product of two projections...
Oh, yeah, okay. All right, yeah. I wanted to come to that. I forgot about that, yeah. Okay. When two propositions are independent of each other, now what does that mean? That means that you can measure both of them simultaneously. It means that the projection operators commute with each other. If you have two commuting projection operators, then the and statement means something. A projection, for example, what doesn't mean something would be to say if you only had one electron. If you had one electron, you could ask, what's the probability that the spin is both up along the third axis and up along the second axis? All right, that would be a meaningless question. You can't do that because the two components of spin don't commute with each other. If you multiply them, take the two projection operators. One of them is 1 plus sigma 3 over 2, and the other is 1 plus sigma 1 over 2, right? Is that the way to write it, or should I put them in the other order? You get a different answer. So there's no meaningful and for the spin is up along the third axis and the spin is up along the first axis. All right? That's a forbidden kind of and. But here we're talking about two different electrons, and all of the operators for one electron commute with all the operators of the other electron. Doesn't matter which order you apply sigma and tau. That's because sigma acts on one of them and tau acts on the other one, and they completely commute. They're completely independent measurements. They don't interfere with each other. Measuring one spin doesn't really do anything to the other one, so particularly if they're far apart. So yes, that's something I should have stressed. Yes, the product is the AND operation, but it only makes sense if the two projection operators or if the two properties are compatible. If the two properties are compatible, which means they commute with each other, then the product is the AND. That was your question? Yeah, okay, good. Good point. Yeah.
One way I've heard this described is in terms of the measurement of one particle imposes a constraint or partial wave function collapse.
Okay,
well,
yeah.
Do you feel that's a helpful way of looking at it? Or is that
Well, I don't know that it's particularly a helpful way of looking at Bell's theorem and so forth, but that's what I wanted to come to. I wanted to come either to the no cloning theorem or the measurement process and the collapse of the wave packet or the collapse of the wave function as being a special case of entanglement. Which one should we do? I think we're better off today doing the no cloning theorem, and then next time we'll talk about the measurement process as a process of entanglement. Entanglement of what with what? The apparatus getting entangled with the system that you're measuring. That's what happens when you do an experiment. When you do an experiment, you may have a dial, not a dial, a pointer that tells you if it goes this way, the spin was up. If it goes that way, the spin was down. You take your electron and you put it into the apparatus, and if the electron is up, then the pointer points this way. If the electron is down, then the pointer points this way. Sounds like entanglement. Sounds like entanglement between the apparatus and the electron, and it is. That's what the measurement is, but we'll come to that. I want to prove a little theorem for you. We're going to have to introduce some additional things. We have not talked about how state vectors change with time. We're going to talk about that next time, I think. But I'm going to tell you one fact about the time evolution of wave functions. Namely, it's linear. What does that mean? That means if you start with a wave function A, and under time or under some process, it transforms into wave function, let's say A prime. And if we start with a wave function B, a different one, and it goes to B prime, then if you start with the wave function alpha A plus beta B, in time it will go to the same linear combination of A prime That's a postulate of quantum mechanics which is certainly experimentally extremely well tested. And what it says is that the wave function, or the state vector of a system, changes in time linearly. Linearly means that superpositions of states transform into superpositions of states in a linear way. That's a postulate of quantum mechanics which is experimentally known to be true to extremely high accuracy. It's the linearity of quantum mechanics. So let me show you what it says about trying to clone systems. Here's our goal. Here's the goal of cloning. Supposing I have a system in any old quantum state, whatever. I want the machine that I can feed it into, and that machine will spit out two identical copies, each in the same wave function that the original one system started with. So it's a cloning operation. And in particular, for example, in fact, whatever the initial state of the system is, it should produce two systems in the identical state. That's the cloning goal, to be able to clone quantum systems. Now, classical cloning is possible. The Xerox machine classically clones information on a piece of paper. It doesn't do it exactly faithfully because little errors happen and so forth, but the degree of error can be controlled, and so you can clone classical systems. You can build machines that whatever state on that piece of paper you put into it, it will produce two pieces of paper with identical information. All right? I actually rediscovered the no cloning theorem a long time ago and called it the no Xerox principle. And string theorists call it the no Xerox principle, no quantum Xerox principle. All right, so all you have to do is prove it for one system. Because if I can prove that I can't, if I want to prove that I can't clone everything, then all I have to do is show I can't clone one thing. So I'll show you what you can't clone. All right, here's my cloning apparatus. It has a port over here that you put stuff into, and it has two ports over here that you take stuff out of. All right, so in goes your system, and out comes two identical copies. All right, let's start with an up electron. Supposing we start with an up electron. So we start with one electron in the up state. Let's just call it up. What do we get out? We get out two ups. Up. I mean, by assumption. All right, so we can say then that the single electron state evolves in time into a two electron state. How it does this, nobody knows. Incidentally, that violates charge conservation, so let's make it neutrons. What? No. You don't. That means energy conservation, but energy doesn't have to be conserved. It can borrow energy from the machine. Okay, but it would violate charge conservation unless it could get charge from the machine, and that's okay. There's nothing wrong with that. But let's just say neutrons and make it simpler. No electric charge conservation.
Say the machine is operated for free, so there's no
What's
charge.
that?
The machine is operated for free, so there's no charge.
Yeah. Okay. So up by itself goes to a state with two electrons, which I'm going to write as up. There's two electrons each in the up state. And I'm just going to write it by putting two ups next to each other. Right? What if I put down in here? What comes out? Two downs, assuming that I was able to build a quantum Xerox machine. And two downs come out. So down will evolve eventually into down. Okay, now supposing I put an electron in. This was an electron that was pointing up along the third axis. All right, so we have our axes again. Now I'm going to put in an electron which happens not to be oriented along the third axis, but what happens to be oriented along the first axis, the x1 axis. All right, so what should I call it? Instead of down, let's call it left, or right. Up, down, left, right, and in, out. Okay, so now I want to put in here a electron pointing to the right, in other words, at 90 degrees along the x-axis, for example. And if I have a faithful cloning machine, I'm not going to redraw the cloning machine. If I have a faithful cloning machine, it should take right to right. Okay, but what is right? What is the right state? The right state is just up plus down divided by square root of 2, right? So what I've actually put in on the left-hand side is up plus down over the square root of 2. Right? Up plus down. But I know what I get out if I put in up. If I put in up, I get up. If I put in down, I get down. If the evolution is linear like this, then that already tells me what I get if I put in up plus down. What do I get? Well, if I put in up, I get up. If I put in down, well, let's write it as I get down over square root of 2. So the linearity of quantum mechanics, the fact that the evolution of states is linear, already tells me what I get if I put in up plus down. I don't have any choice. Right? But what is right? Let's see if it agrees. What does right mean? Right means up plus down for the first electron times up plus down for the second electron. I'm just juxtaposing them by the two electrons. The first factor corresponds to one electron. The second factor corresponds to the other electron. Sorry, over square root of 2. Okay, but when I multiply this out, what do I have here? I have a configuration with two ups, up times up. I have a configuration with two downs, but I also have up, down, and down, up. Unavoidably, if I take two electrons, each with spin along the x-axis, I will find, if I measure the third component of spin, that some of the times I will find an up and a down. Over here, I have two ups and two downs, but never an up and a down. So you see the, the assumption that you can build a cloning machine which both clones ups and downs and also clones lefts and rights is inconsistent. It's inconsistent with the linearity of quantum mechanics.
But what if you insist that the two outputs have to...
Say it again.
You seem to be assuming that the two outputs have to be independent of each other somehow.
Yeah, I'm not sure what it would mean to clone things unless they were cloning things, two independent things. Well, sorry. The assumption was that up produces two ups, and a down produces two downs.
Yeah, but then you explain the right to be the product of the...
So that's the way you build composite states. That's the way you build states of independent systems, is to multiply the state vectors in that fashion. It's called taking, we haven't had a time to do everything. Unfortunately, we haven't had time to do everything. But the mathematical operation of combining systems is called tensor product. You take the tensor product of state vectors. And that's what this is. This is the tensor product of two rights. And then you expand it out, and you see what you get. And what you get cannot be this. So you're right. There's a degree of assuming that the two things are independent of each other. But I'm not sure what it would mean to clone things if they weren't independent of each other, and then you could do independent experiments on them. So it is not possible to take a object in an arbitrary wave function and put it into a machine and have it come out as two replicas of the same thing.
A laser is a pretty good cloning device. So where does your argument break down for a laser?
A laser is a cloning device. Why is
You put in a photon that has a certain state, and you're going to get a bunch of them produced.
It's actually not true.
Okay.
Stimulated emission, the polarization of the output pair of photons is not quite the same as the input photon. The vector is the linear combination of the initial magnetic state of the excited atom plus the incident stimulating photon. So while the two output photons are identical, they're not the same polarization.
I have to think about the question. You may be right. I have to think about the question. So you say you take a photon with a given polarization and you stimulate some emission. I have to think about what the...
If you analyze it from an information point of view, if the information of the excited atom contributes to the output state, then that is noise from a cloning point of view.
You may be right. I have to. I'll think about it this week and see if I can give you a simple argument. However, there is no controversy about the fact that you can't build a cloning machine. I think there is I don't even know if it's controversy. I think there's a question of how close you can get. How close can you get to a cloning machine? And I've seen papers saying different amount, some quantitative measure of how close you can get. And there's some number like 3/4 that come out. You can have a cloning machine that's 3/4 accurate or some such thing. But that's something I don't know much about. Anyway, this is the basic idea that you can't have and the reason is simple. Multiplying two things together like this, taking anything and squaring it, is not a linear operation. It's a quadratic operation. You take any state, basically, and replicating it is sort of is a sort of operation which is quadratic. Right? It's an operation of not squaring something, but sort of multiplying it by itself. That's what's going on here. That's what's going on here. And that's simply not a linear operation. It can never be linear. It's always quadratic. And since all the evolution of state vectors is always linear, you can't do it. You can build a machine that will clone ups and downs, but then it won't clone rights and lefts. You can build a machine that will clone rights and lefts. It won't clone ups and downs.
This prevents transfer, right? You can not duplicate, but you may transfer these properties to another.
Yes. That's a different issue. That's a different issue. That you can transfer some information from one thing to another. Yes, but what you can't do is duplicate it in two systems. Right, so you might have some kind of information. For example, the electron is up, and you might want to transfer that to a photon and send it, and the question is how well can you transfer it to another system, and that's a separate question. Yeah?
And this whole discussion, I think you have to state somehow that you don't know the state of the particle when you try to clone it. If you know it, if you know the state, then of course you can clone it. So
if you know the state, you can build a machine that will clone it. But it will be a different machine than so for example, if I know the state is up, I can build a machine that will clone it. And the same machine will clone down. If I know the state is right, I can build a machine that will clone it. But the same machine will not clone ups and rights. So yes, if you know the state, you can build a thing that clones it. Was that the question? Or answer? Or was that?
If you don't know the state, then you cannot clone it. You have a certain particle; it is in a certain state.
All right, but let me just say, but let me just say it a little differently. Let me say it a little differently. You cannot build a machine that will clone anything, or that will clone ups, rights, or ins and outs. The same machine cannot clone them all. So if you didn't know what the state was, somebody gave you a state and said, no, you don't look at it, and you just say, I want to clone it. Your machine may just happen to clone it because it may be the up thing. But the chances are, well, it wouldn't clone things. I've said it enough times. I can't say it again. I'm running out of steam.
Right. The output of the machine would be what you wrote down the last one.
Yes. But that's different than what the output of the machine has to be by quantum mechanics.
That's the linear result.
This is the cloning result. This is the linear result. Right. Yeah. And they're different. So they can't be the same. Right. In other words, just two electrons, both right, have in them a piece with an up-down and a down-up. That's inconsistent with what the linearity of quantum mechanics says. So, sorry, no cloning.
When I see this, it seems like the amount of information containing two independent entities is different than an entangled entity. And
yes, this is true.
When we see it, has like anybody tried to attack this from that perspective of information theory?
I'm sure they have. The last time, what I told you is if you have a single electron, the state vectors are a two-parameter family. If you have two independent electrons, which have never been entangled or anything like that, then the state vectors you would expect to be a four-parameter family. But in fact, the state vectors of two electrons are a six-parameter family, so there's a richer class of states. Now, do you want to, can you quantify that by information theory? I don't know, I haven't, I'm sure you can. Well, I certainly know how to quantify the degree of entanglement of two systems. There's something which I hope we will get to, which is called entanglement entropy. And entanglement entropy is a measure of the degree of entanglement of two systems. So we can certainly quantify the amount of entanglement between two systems. I'm not sure if that's what you're asking. But in any case, we'll try to get to that concept of entanglement entropy. Okay, any other questions before we go home?
The preceding program is copyrighted by Stanford University. Please visit us at stanford.edu.